In this tutorial, I just want to cover the Arrhenius equation, which basically this is used to calculate the activation energy of a reaction. Now, the activation energy of a reaction is just basically the minimum energy needed for two molecules to react. Another way of putting it is just the energy needed to have a reaction begin, so that once you reach that particular amount of energy, then a reaction will start. Now, you're able to do this by using something called the Arrhenius Equation, which just basically expresses the dependency of the rate constant on the temperature. Now, if you were to look at the equation, which I have here below, on one side you're taking the natural log of two different rate constants, one at initial temperature, which is this one right here, and above that is the rate constant of that same reaction at a final temperature. And that's going to be equal to your activation energy, which is just EA, over your constant, which your constant is just 8.31, which you may have, which is also one of the gas constants that you could possibly use. We used a different one before. And that's multiplied by 1 over the initial temperature minus 1 over the final temperature. So now let's just walk through one of the examples that you could possibly have. In this case, what I recommend, just as I recommend with all the type of problems that you do in AP Chemistry, is just to go through and figure out what number goes with which thing. So for instance, in this case, you can see that you have a rate constant of 2.7 times 10 to the negative 4, and that is at 600 K. And you also have another rate constant of 3.5 times 10 to the negative 3 at 650 K. So you saw a jump in temperature between the two times, the two reactions. What you need to do is find the activation energy, and then once you find the activation energy, then you'll calculate the rate constant at a different temperature. So what you need to do is use the Arrhenius equation twice in this case, once to find the activation energy and then another time to figure out the rate constant at 700 K. So to do that, let's just walk through this. You have your natural log of K2, which in this case K2 is going to be the 3.5 times 10 to the negative 3, and that's going to be over the K1, which is 2.7 times 10 to the negative 4, equal the activation energy, which is what you're looking for, over your R, which R is just 8.31, times 1 over K, the first temperature, which is your initial temperature, which is 600, minus 1 over the temperature that you ended off with, which was 650. So now just do out this math, and if you were to do out, the left side, you end up with a number of 2.562 equals EA over 8.31, and then if you were to do the math within the parentheses, you end up with 0.000128 for that. Now just continue on solving for your x in this case, which if you do that, you have 2.562 equals 1.54 times 10 to the negative 5 EA, and then if you were to solve for EA, it's just equal to 1.66 times 10 to the negative to the positive 5, and that's going to be in joules per mole. So that takes care of your activation energy. Now you have to go back and figure out your rate constant at 700 K, which you'll use this activation energy that you just figured out within your Arrhenius equation. So now let's set up the other Arrhenius equation, which in this case you have the natural log. K2 you don't know, that's what you're looking for, and that is going to be over the initial that you had before, which is 2.7 times 10 to the negative 4, equals activation energy in this case is what you figured out in the previous calculation, which is 1.66 times 10 to the 5th. That's over your constant, which is 8.31, times your initial temperature, which is 1 over 600, minus the temperature that you're trying to get to, which in this case is 700 K, so you'd put it 1 over 700. So now go about figuring this out. What I recommend first is that you just take your right side and figure out all the math in that case, which if you were to do that, you end up with 4.76 equals the natural log of K2 over 2.7 times 10 to the negative 4. Now what I recommend is just taking the anti-natural log. So you would have, if you were to go and do that, you'd end up with K2 over 2.7 times 10 to the negative 4 on this side. That would be equal to E to the 4.76. And if you continued with this math, you'd end up with the K2 equal to 0.0314. So that's again just basically taking your Arrhenius equation, first looking for the activation energy, and then after that looking for the rate constant at a specific temperature.